Hi friends, welcome to our video on computing the last digit. In this video, we are going to study how we can find out the last digit for large computations. Now, this is not only a question in itself. I mean, in some of the aptitude tests, this could be asked as a direct question in itself. However, you can also remember this technique to figure out, just in case you're faced with a large computation and the aptitude test question has 4 or more choices and you got to figure the answer without the entire computation, then you can use this method and arrive at the right answer. Alright, so let's start. Now let's say I have this computation, a very simple computation, 4 plus 5. Clearly this is 9, yeah, but if let's say I were to extend this computation to something like 284 plus 495, now this has to have some hundreds, some tens, but the last digit, the ones digit, is always going to be 9. And how this is done, any simple computation, right? 284, we are going to do this. We are just using some primitive computation, primitive addition method. 495, we notice that the last digit is only dependent on the last digits of the numbers being added, right? So we get a 9, and if there were to be some carried over these digits, so the 2 and 8 in the 284 and the 4 and the 9 in 495 do not impact the last digit. Okay, so that's exactly what we are going to use. Now let's say the computation were to go something like this: 4898 plus 384, right? So you just seen that these digits 489 have no impact whatsoever on the last digit of my answer, so I got to ignore these, right? And in this number 384, I got to ignore 3 and 8, right? So 8 plus 4, that should give me my last digit. However, 8 plus 4 is 12, yeah? So I cannot write the entire 12 here, so I'll just use 2 because 1 gets carried over and we do not account for it when we are computing the last digit. Okay, likewise, so this is how finding the last digit in an addition goes. Likewise, finding the last digit, let me just write addition here. Okay, now likewise, let's find the last digit in subtraction. Okay, so this is a sample subtraction computation. So let's say I were to subtract from 15, let's say I were to subtract 12. So how a traditional subtraction would go, I would write 15 here and I would write 12 here, and when I subtract, the last digit, the units digit of this computation is only 5 minus 2, which is a 3. I don't care what happens here, right? So just like in addition, I would just subtract a 2 from a 5 to get 3 in the units place, right? So I don't care what happens here because I'm meant to find only the last digit. Okay, next, if let's say I were to have a larger number, I would do the same thing. Let's say I have 4895 minus 382. Again, I would ignore 489 of the 4895 and I would ignore 38 of the 382, and I would just figure the 5 minus 2 as my last digit, right? Okay, however, what happens if the last digit of the number from which the other number is going to be subtracted is smaller? Let's say if I were to have 4892 minus 385. So just like I would ignore 489 here, I would ignore 489 here, and just like I would ignore 38 here, I would ignore 38 here. However, the 2 minus 5 gives me a minus 3, yeah? So I cannot have minus 3 as my last digit, right? So this I will not do. However, in a subtraction, I would carry 1 from 9 and give it to the last digit. So essentially, when I'm doing a simple subtraction, I would subtract 5 from 12 and not 2, right? So that's exactly what I'm going to do. So if this digit is smaller than this digit from the one which is being subtracted, I would just give it a tens, I would just give it a 1, so I would subtract 5 from 12, so the last digit of this computation is 7. Okay, so this is how addition and subtraction go. Now let's move on to multiplication. So in case of a simple 4 times 7, yeah, it is 7 for the 28, so my last digit is 8. Yeah, that's not a problem. However, if I were to have a bigger number, let's say I were to have 4894 times 387. So when I were to do it in the traditional way, I would have 4894 times 387. So just pay attention to how this works. So 7 times 4, 28, and then I carry 2. I would have 7 9 the 63 and 2 5 and carry 6 and so on, right? And then I put a cross here, and then I start with 8 times 4, 32, and then I carry 3 and so on. Yeah, and then for multiplying 4894 by 3, I put 2 crosses here because it is 300 that I'm multiplying it with, and this is 3 for the 12 and carried 1 and so on. So in the answer, I notice that my units digit is 8, yeah, which is the units digit of 7 times 4, right? So again, just like in addition and subtraction, it does not matter what is there from the tens digit onwards. Okay, likewise here. So the last digit, the units digit of this product is going to be the units digit of 4 times 7, which is 8, right? Okay, now with this basic theory in place, we are now going to move on to the next, to the higher level, where we would explain how the large multiplications work. Okay, now in terms of large multiplications, what I really mean to say is, let's say if we were to compute a power, a very high power of 4894, yeah, let's say we give this a very arbitrary large power, 287. Let's say we were to find out what the last digit of this product going to be. Okay, so now to understand this, we first have to understand the cyclicity of powers. Okay, now in terms of cyclicity, let's say I have a number whose units digit is 1. Let's say I have a number 21. Okay, now 21 to the power is 21. However, 21 to the power 2 is 21 times 21, right? So I have 1 1 the 1 and something here, right? I know it's 21, but I'm ignoring it. Okay, and then I put a cross here and 2 1 the 2 and then something here. My last digit is 1. So I've just did this computation. 21 square is nothing but 21 times 21. So the last digit of my answer, so last digit of 21 to the power 1 is 1, and 21 to the power 2 is also 1 times 1, which is 1. Okay, likewise 21 to the power 3, this is 21 times 21 times 21. So the last two digits, the last digit of this computation is 1, then last digit of this computation times the last digit of this number, which is 1, gives me another 1. So you notice that no matter what the power of this number, my last digit of any power of 21 is going to be 1. And for that matter, I can extend this logic to any number, however large, but the last digit being 1. Okay, so let's say, so if I were to express this, I would say that 148971, I've just taken an arbitrarily large number to power 4872. Yeah, so an arbitrarily large power, an arbitrarily large number. However, if the last digit is 1, I just have to say that the last digit of the result is going to be 1 and nothing else. Okay, now you would notice that the same logic, last digit 1, the same logic extends to 0, it extends to 5 and 6 also. Yeah, so any number with last digit 0, any power of that number, let's say the number is 4720, okay, any power of this number, let's say 784, what's the last digit? Clearly 0, no question, right? Likewise, last digit 5, give any arbitrary number, 498275, give it any arbitrary power, 874, has to be, last digit has to be 5. Yeah, look at the powers of 5, 5, 25, 125, 625, and so on. Any power of 5 would end in 5. Okay, the result would end in 5. And likewise for 6, the powers of 6, they go like this: 6 times 6 is 36, last digit is 6. Okay, then again 6 times 6, so it continues in the same way. So any arbitrarily large number, 4896 power 1003, last digit 6, any power, the result would have units digit 6. Okay, so we have seen that for the numbers 1, let me write 0 here, 0, 1, 5 and 6, if the last digit is any of these numbers, the power of this number with last digit any of these is going to be the same. Okay, so the last digit, this would give me 0, any power, this would give me 1, any power of this would give me 5 and in the units place, and any power of this would give me a 6 in the units place. Okay, so this is how 0, 1, 5, 6 in the last digits they work. All right, but let's move on to the next idea. Now here, let's see how the last digit of a number ending in 4 works. Okay, so let's say 4. So the first power of 4, units digit 4. However, the second power of 4 is 16, so last digit 6. Okay, let's see the third power of 4. This is 16 for the 64, so we're back to 4. Okay, and then the next um, fourth power of 4, so 64 times 4, clearly the units digit is going to be 4 times 4, 16. Yeah, and this is 6. So I notice that if the last digit of any number being 4, if this number has an odd power, the last digit of the result is going to be 4. Okay, likewise, if I have any number last digit 4 but having an even power, the last digit is going to be 6. Okay, so here the last digit 4 has displayed a cyclicity of 2. Okay, now the next digit in this vein, in this line, the other digit which works exactly like 4 is 9. Okay, let's see how the powers of 9 work. So the first power of 9 is clearly 9, last digit 9. The second power of 9 is 81, last digit 1. Okay, now the third power of 9, it would be 81 times 9. Okay, so 81 times 9, the last digit of this result is going to be 1 times 9, which is 9. Okay, so I get a 9 again, and the fourth power of 9 is going to be whatever number, right? So this number which ends in 9 times 9, so the last digit of this product is going to be 9 times 9, 81. So 1 of 81. Okay, so I notice that just like 4, last digit 9 also has a cyclicity of 2. Okay, it has, for every odd power of the number ending in 9, okay, the last digit of the result is going to be 9. Likewise, any even power of the number ending in 9 would have the last digit 1. Okay, so we would say that 4 and 9, they have a cyclicity of 2. Right, now let's move on to the remaining digits, and they are 2, 3, 7 and 8. So let's say how 2 behaves. So any number ending in 2, okay, if I give it power 1, the last digit of the result is going to be 2. Okay, so let's say powers are moving in this direction, last digits are moving in this direction, and in this table I'm going to mark how the last digit of this result going to be. Okay, so let me just draw this table. So power 1, last digit of the last digit 2 is going to be 2. Likewise, if the power is 2, then the last digit it's going to be 2 times 2, 4. Okay, when the power is 3, the last digit is going to be 2 times 4, 8. And when the last digit is 4, okay, I would have the last digit of this 2 to the power 4 as 2 times 8, 16. So I'll just write a 6 here. Okay, so the last digits of the power 2, they move like this: 2, 4, 8, 6. Now what happens when I give it 2 to the power 5? Now 2 to the power 5 will be 2 times 6, 12. Okay, so we have come back to where we started. So you notice how the powers of 2 would go: 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and so on. So you notice that the powers of 2, they move like this. So there is a cyclicity of 4 involved here. So every fourth power, the last digit starts to repeat itself. Okay, so let me just say for powers 1, 5, 6, 7, 8, and then 9, and then 10, and then 11, and then 12, and so on. Okay, let's say how this works for 3. Now 3 to the power 1 gives me 3. 3 to the power 2 gives me 9. 3 to the power 3 gives me 27, so I'll just write the 7. 3 to the power 4 gives me 81, so let me just write 1. Now as soon as I get a 1, 81 times 3, the last digit is going to be 1 into 3, I come back to 3. Yeah, so just like it worked for 2, every fourth power, the digit starts to repeat. Okay, likewise for 7. So for 7 it goes like this: 7, 7, 7 the 49, so I'll just write 9, 7, 9 the 63, so I just write 3, and 7, 3 the 21, so I just write a 1. And as soon as I get 1, I'll multiply 7 by 1 and I get a 7 again. Okay, and likewise for 8, I have 8, 8, 8 the 64, 8, 4 the 32, 8 to the 16, 8, 6 the 48, and I come back. Okay, so if I were to illustrate, let's say I have a large number 487. Okay, and I have to find out the last digit of the power 487 to the power 10. Okay, so I notice that for 7, the power 10 has a last digit 9. Okay, so the last digit of this computation is going to be 9. So let's take another example. Let's say 4898. Okay, the last digit is the power is 7. Okay, so last digit 8, so power 7. So I'll just find it in this table. This is 8, last digit 7. I have the answer would have the last digit 2. Okay, hope this is becoming clear. If it is not clear, feel free to rewind the video and watch it again. All right, now can I generalize this table? Now to generalize this table, all I would need to do is I'm writing the last digit of whatever number whose power I'm going to find. So for 2, 3, 7, 8. Okay, now you would notice that 1, 5, 9, they're all in the form 4n plus 1, right? So if I can figure out my power, if I can divide the power by 4 and find that the remainder is 1, then the last digit of the answer is going to be 2, 3, 7, and 8. Okay, likewise, if the power is of the form 4n plus 2, you will notice that 2, 6, 10, this is a arithmetic progression, common term 4n plus 2. Okay, So I would have the units digit of the answer as 4994. Okay. Likewise, if I have 4n plus 3, if I have the power in the form 4n plus 3, I would have my last digits as 8, 7, 3 and 2, and likewise this is all 4n. If I have the power in the form 4n, my last digits are going to be 6, 1, 1 and 6. So let's get back to a very complicated computation. Let's say I have a large computation, a large number 28927, okay, and if I were to find out its 103rd power, okay, so clearly the last digit of this computation is the same as the last digit of 7 to the power 103, because I know that these digits, they don't matter. Okay, now for 7 I know that the cyclicity, it repeats every fourth power, it repeats. Okay, so I just have to break 103 in the form 4n plus something. Now I know that 103 is equal to 100 plus 3, where 100 is a multiple of 4. So I can just write this as last digit of 7 to the power 4n plus 3, because that's what 103 is. 103 is of the form 4n plus 3. So I'll just find 4n plus 3 and 7, the last digit of this computation is 3, and that's my answer. Okay, I hope this is clear. Please feel free to watch this video again. I believe you may need to watch this video a few times, but before you do that, let me just summarize the entire cyclicity business for you. Okay, so this is cyclicity table, right? So let me write down these last digits in order: 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So the cyclicity of 0 is 1, okay, which means any number, any power, you will get the result will be a 0. Okay, likewise for 1, again the cyclicity is 1, so the result would have, so last digit, let me just clarify, last digit of the result, last digit of this will be 1. Okay, likewise cyclicity of 5 and 6 is 1, so last digit 5 and 6, no change here. Okay, now cyclicity of 4 and 9 was 2. Okay, so if the power is of the form 2n plus 1, okay, so 2n plus 1, you would get a 2. If the power is of the form 2n, right, odd power, you would get a 2 in the last digit, even power, you would get a, oh I'm sorry, okay, so if the power is odd, last digit 4, power odd, you would get a 4 in the last digit, and power even, last digit 4, you would get a 6. Likewise for 9, if the power is odd, you would get a 9 in the last digit. If the power is even, you should get a 1 in the last digit. Okay, for the remaining 2, 3, 7 and 8, the cyclicity is 4. Okay, so whenever it is 4n plus 1, you would get a 2 here, 2 to the 4, 4 to the 8, 8 to the 16 and then back again. So you have 4n plus 1, 4n plus 2, 4n plus 3 and 4n. Likewise for 3, you would have a 3, 3 3 the 9, 9 3 the 27, 7 3 the 21. Okay, and for 7 and 8, let me just write again, 4n plus 1, so for 7 you would have 7, 7 7 the 49, 7 9 the 63, 7 3 the 21. Okay, and for 8 you would have 8, 8 8 the 64, 8 4 the 32 and 8 to the 16 and then back again. Okay, so you can just try and remember this table. If you are able to remember this table, you would find that you know, your computation of any large powers of digits ending in any of these digits is fairly simple. Okay, Thanks for watching.